Hello everyone. In this video, I am going to demonstrate how to use Power World Simulator to do transient stability analysis in power system. In this problem, it is assumed that a generator supplies power to an infinite bus through double transmission line. The voltage at the infinite bus is 138 kilovolt. The generator generates power at 11 kilovolt. Transformers step up the voltage 11 kilovolt into 138 kilovolt. It is assumed that there is a three-phase solid fault occurs at bus 4 at the time of 5 seconds, and also assumed that the fault is cleared at the time of 5.05 seconds by opening one transmission line, and it is going to verify whether the system is stable or unstable after occurring the fault and after opening the transmission line. Synchronous machine model and constants. For transient analysis, we have to choose simple machine model for our analysis. Here I am selecting Gen CC model of synchronous generator. Here we can see the different parameters in the machine model: inertia constant, damping factor, armature resistance, quadrature reactance. Likewise, there are so many parameters. Here it is very essential to select machine constant R, that is machine model, to do the transient analysis in Power World Simulator. Transient contingencies. Here we have to select set of contingencies to do the transient analysis. Here we assume the fault occurs at bus 4 at 5 seconds and it is cleared at 0.05 second by opening the line. It starts from 2 to 4 in the circuit. And also we plot the swing curve for different fault time, how the rotor angle, that is the torque angle, varies with respect to time, accelerating power PA. It is the difference of PM minus PE, power mechanical and power electrical. And also we plot how the megawatt variation happens in the system. Now we verify the result using Power World Simulator, how the transient response when the fault occurs at bus 4 of our system. Now we select File, go to New Case. Now we draw our model first. Select bus 1, which is operating at 138 11 kilovolt. Bus 2, where we connect a step-up transformer. It is operating at 138 kilovolt. Bus 3 is at 138 kilovolt, is the infinite bus. Bus 3 is the infinite bus. Bus 4 is the bus which is connected between bus 2 and 3. Now we connect a double transmission line from bus 2 to 3, having 0.7 per unit reactance. Now another transmission line two to 4, having 0.5 0.5 per unit reactance. Then transmission line from 4 to 3 having a reactance of 0.2. Now we connect a transformer between bus 2 to bus 1 having a reactance of 0.5. Now we connect a generator at bus 1 display position left side. Now we connect another generator at infinite bus. Actually, infinite bus is also considered as a generator which is connected at the right side. Now we have to select this 3 as an infinite bus as a reference bus system slack bus. Now to make this system 3 bus 3 as a slack bus, follow the procedure. Go to run mode, add on transient stability, go to option power system model. Here infinite bus modeling, no infinite bus. Now model the power flow slack bus as infinite bus. Now this bus 3 acts as a slack bus. Next step is we have to supply power to infinite bus from the generator. I choose here per mouse click 5 megawatt increase or decrease in power. We can increase or decrease by clicking the up down arrow from generator. Now this generator supplies power to the infinite bus. Go to tools, run. Now the generator supplies power to the infinite bus. We can increase the power or decrease the power. This is the first part of simulation in which we model the entire power system for transient stability analysis. The second part is the fault which occurs at bus 4. Now we visualize what is the power it's flowing through each line. Go to edit mode, draw, field, transmission line field, megawatt flow, field, transmission line field, megawatt flow, field, transmission line field, megawatt flow. Now we can see what is the power it is flowing in the double transmission line. Here the power generated is 60 megawatt. The power flowing in each line is 30 megawatt. We can decrease and increase the power. Here the power supplied by this generator is 100 megawatt. The power received by the infinite bus is minus 100 megawatt. Now we move on to the next part of the simulation is transient stability analysis. The first step of the transient stability analysis is we have to insert the machine model. Stability, insert machine model. These are the set of machine models available in Power World Simulator. Here I choose Gen CC model. Here we can see the lot of parameters: inertia constant, damping factor, armature resistance, reactance, synchronous reactance, direct axis, quadrature axis, like that. So many things are there. We have to insert one mission model to do the stability analysis, transient stability analysis. Now second step is we have to fix the amount of power it is flowing in the line. Here I have choosing the power which is flowing is 30 megawatt is flowing in this line. Here 15 and 15. For this 30 megawatt, what is the transient response that we are going to study now. Now go to add-on, transient stability. Now we do the simulation. Here simulation, the time it starts 0, time it ends 10, I make it 50. Now we have to select the transient contingency elements. Now insert. So our transient contingency, first one is the fault occurs at bus 4. So here object types are here. We have to choose bus 4. The time the fault occurs is, we are taking 5 seconds. Apply fault or clear fault. Here we have to choose apply fault. Type of fault, balanced 3-phase fault. There are different options are there. Here we are taking balanced 3-phase fault, solid fault at bus 4 at the time of 5 seconds. Second, once the fault occurs, we have to clear the fault by opening the transmission line. So branch transmission line, it is connected 2 to 4. So where the fault occurs, we are going to open that line and we are going to verify the result. I am opening the transmission line after 0.05 seconds. 0.05 seconds. Now open the line, open both end, give OK. Now we have to add the plots. We have to plot the parameters that varies during fault and after fault. The rotor angle or torque angle. Second thing, megawatt acceleration, how much the power acceleration happens. The third one, megawatt, how much the power flow varies from the generator to infinite bus. These three things we are going to plot on execution of a run. Now we can run our system. Transient stability. Here we can see there is a steady state from 0 to 5 seconds till the fault occurs. Once the fault occurs, the system parameter changes and it settles down to a new value. Here we can see the rotor angle. Rotor angle, it is around 22 to 24, between 22 to 24, and it varies and it comes and settles down near to 30 degree. The power which flows from generator to infinite bus is 30 megawatt. There is oscillation in the power that also settles down to 30 megawatt. Here you can see the megawatt acceleration happens that is the power between the power mechanical and power electrical. Initially it is 0. Once the system get disturbed, there is a change in megawatt acceleration. After that it again comes to 0. Now we can do this simulation for different timing. Here I am choosing the time I open the circuit breaker within 0.05 second. We can choose 6 second. If I open the circuit breaker after 1 second, what happens? The same similar thing happens here. It is at steady state. Once the fault occurs, there is a huge transient happen in the system and it is settled down to a new value, and we can find here the rotor angle or torque angle. It is not increasing enormously, it is within the limit, so we can say the system is still stable. Now we can increase the time 9 seconds. That means after 3 seconds, after 4 seconds I am opening the circuit breaker. In this case we can identify the torque angle is increasing enormously and it reaches the unstable state. Now the synchronous machine lost its stability, lost its synchronism. Similarly, we can do the analysis by changing the power, megawatt power, and the time of opening of circuit breakers for different value of power. Here I did for 30 megawatt. We can increase the power 40 megawatt. What is the transient response analysis by plotting the swing curve and megawatt variation. All these parameters we can note down for the fault occurs at bus 4 when we transmit 40 megawatt power, and also we can do the same for 50 megawatt power also. This table shows the solution of the above problem. The power generated, column 1 indicates the power generated by our generator, 30 megawatt, 40 megawatt, 50 megawatt. Second column indicates maximum number of cycles to clear the fault. Here up to 180 cycles, system is stable. The fault occurring time is 5 seconds. Fault clearing time is 8 seconds. So 5 to 8 seconds the system is stable. Above 180 cycle, above 8 seconds, system becomes unstable. So if we transmit the power of 30 megawatt, if any fault occurs at bus 4, we should open that circuit breaker before 8 seconds. If we open after 8 seconds, system becomes unstable. The similar thing is established for 40 megawatt and 50 megawatt. For 40 megawatt case, up to 5.6 system stable, above 5.6 seconds system becomes unstable. Same for 50 megawatt, up to 5.3 seconds, 5 to 5.3, within 0.3 seconds. That means within 18 cycle we have to open the circuit breaker, otherwise the system reaches the unstable state.